All right, first we will look at how to change a Cartesian equation into a polar equation, and the reasoning behind that is we're more familiar with what these Cartesian graphs look like, and also I think it's a bit more straightforward. So x equals 3, right? That is a vertical line. It's not a function, which doesn't matter in this point, or in this example. But all we have looked at so far is like how to get a point, right? How to get a polar coordinate from a Cartesian coordinate. So for instance, the point 3, 0 was identical because the radius is 3, angle is 0. But what about all of these other points, right? How do we get a collection of points? So we use these substitutions that we had talked about. X equals r cosine theta, y equals r sine theta, and there's also an x squared plus y squared equals r squared we may need to use as well. So I want to start with an easier one. X equals 3, I will simply substitute r cosine theta for x, right? X is equivalent to this, okay, equals 3. And in a polar equation, the goal, okay, always our goal is to solve for r. Okay, r equals stuff, without another r. Just like in a Cartesian, right, the goal is to solve for y. So in the second example, right, I recognize this is linear. I would do some work and I would get y, I'd isolate y. And then I would have a form y equals mx plus b, and I could graph it. Okay, so in polar, our goal is to isolate r. So therefore, r cosine theta equals 3. I want to divide that cosine theta to the other side. And our answer then is r equals 3 over cosine theta. That is the equation of that line. Now, remember, just like in a Cartesian, we have two variables, an independent variable and a dependent variable, x and y. And as x changes, y changes. Same thing here. As theta changes, r will change. All right, so you start to substitute different angles in for theta, and our r will increase. Right, the larger theta becomes, r will increase as well. So create a bigger angle, we have a larger r. Up until there's a problem, right? We can't divide by 0. So even though we're in polar, we still can't divide by 0. So theta would have a problem at pi over 2. And that's why, right, I can never get to this angle pi over 2. It's impossible to get this vertical line where x equals 3. I can never have that angle of 90 degrees. And the equation speaks for itself. That would give me undefined. So, works out. Alrighty. In this next one, we don't need to solve for y. I was simply saying in a Cartesian coordinate, right, Cartesian equation, we do. That's how we would graph this thing. We could plug it in a calculator, get it that way, or we could do test points, but usually we solve for y in any equation to see if it's a function. So if we did that here, we would have, 7y equals negative 2x minus 3, divide 7, so negative 2/7 x minus 3/7. So then I know, right, my y-intercept here, my slope here. Quick rough sketch of that. So y-intercept at this -1, it's somewhere down here. And then down 2 over 7. So there's -1, -2, somewhere here, and then over 7, not to scale, right? Again, rough, very rough sketch, just so we kind of see what's going on. All right, so we have that line. Like I said, we don't need to solve for y. In fact, it is not going to save us any work at all. So let's immediately just make those substitutions. X is our cosine theta, so we have to polar, we have 2 r cosine theta plus 7 y is r sine theta equals -3. Remember, the goal is to solve for r. Well, if we have an r here and an r here, the easiest way to do that is factor it out. So what am I left with? I'm left with 2 cosine theta plus 7 sine theta, okay, equals -3. And solving for r, we just divide all this stuff out. I'm just going to be lazy and do that because I'm going to write my final answer in the next line anyways. R equals -3 over 2 cosine theta plus 7 sine theta. All right, at this point, you're probably looking at both of these and like, why, right? Why would, seems such a waste of time. Why would I do that? So before we do this last example, let me break it down a little simpler and explain why we would do this. So I'm going to squeeze it in on the left here. X squared plus y squared equals 4. And then you'll see the more complex it gets, like the last example with 4y, the more work it would be. In a Cartesian coordinate system, we have to solve for y. Okay. Now, some of you may recognize this like, oh, that's a circle centered at 0, 0 with a radius of 2. Okay, you're correct. But as a function, right, we need to solve for y. So kind of 4 minus x squared or -x squared plus 4, either way. But at this point, when you take the square root, remember that square roots have 2 roots. It's a plus or a minus. So now you have 2 functions. Y equals positive square root 4 minus x squared, and that describes this upper half. And then y equals a negative 4 minus x squared, and that describes this lower half. And as we progress through math, these, not only like did I have some work to do to find the 2 functions, these often are more difficult to work with. They're ugly, they get more complex, especially as I add more. Like the right equation with that y just adds another step to this, and they become more challenging. Remember, in polar coordinates, we had said x squared plus y squared equals r squared. So right away, I could make that substitution, r squared equals 4. So therefore r, yes, I still get 2 equations. I get a plus or a minus 2. But if you're telling me r is 2, and you don't tell me theta, that means theta could be anything, right? Then that describes this entire circle. Because remember, the radius being 2, right? I go out to 2 units, and theta could be anything. R is -2, very similar. I'll just go, right, -2 units. And again, theta could be anything. I get the same circle. Even though this circle example isn't horrible, I'd say r equals 2 or r equals -2. You can see, right, that is much simpler to work with for anything. Okay. Now, x squared plus y squared equals 4y. I have no idea now what this looks like. In fact, Cartesian coordinate system, I'm going to have to subtract 4y and then complete the square and then try to find the center and the radius. Okay. there's some work involved. Well, let's try it polar coordinates. Let's see if it makes it any easier. Again, x squared plus y squared, r squared. We know y, it's r sine theta. So we have r squared equals 4r sine theta. I need to isolate r. So the only thing we could do is subtract the entire thing. So we'd have the r squared on the left minus 4r sine theta, right? Bring it to the other side, equals 0. Factor out an r. What are we left with? We're left with r minus 4 sine theta. Okay, now we have two equations, r equals 0, which that doesn't really do much. So what is that? Well, we haven't really talked about what if r is 0. Well, radius 0, right? I'm here. Any angle. Okay, create any angle, you're still at that origin, right? Or in polar coordinates, we call this the pole. 0, 0 is the pole. So that doesn't do us any good. I highly doubt x squared plus y squared equals 4y. The only solution is 0, 0. So therefore, r minus 4 sine theta equals 0, and r equals 4 sine theta. Look how simple this is, and we don't even have plus or minus, right? I have one equation, r equals 4 sine theta, to describe that graph above. Now, graphing this at this point, we could pick some values and see what's going on. Most often, though, we use technology to graph polar equations because they become really quite complex, and they really look amazing too. If you have a graphing calculator, go into your mode and change it to polar and try graphing this. Or GeoGebra, it does accept polar coordinates as well. I'll do that in a separate video. So try graphing r equals 4 sine theta in GeoGebra. And it should still be a circle. I don't remember. I should have graphed this before, but I bet it does this. Okay, up at 4, if I remember correctly.